Hey everyone, welcome to Your Desk University. We are a group of computational designers and software developers in the AEC community that really wanted to come together to not only educate, but also unite the computational community in the AEC industry. And we know that you are one of those people. And with that, we are today going to learn about the Lucas Museum of Narrative Art. And I'm personally fascinated because if you saw the image, it looks like a spaceship, but somehow it was meshed for that seamless nature. And I can't wait to hear from the tech experts today to hear about how they went about doing that. Of course, if you're involved in computational design, you probably have an idea that has something to do with Grasshopper, but really telling us the tool isn't necessarily telling us how. And we're going to dig more into that. So with that, I do want to see and get to our speaker. This is Georgios. I really just but I'm blessed to have him as a coworker. It's fun on Your Desk University to talk about all kinds of people, but it's also fun sometimes to talk about people that work at my firm. And Georgios and I worked together on the AU Design Slam and a couple other projects over the last year, and I'm great. Georgios, can you tell us a little bit about yourself? Maybe a hint about an extreme sport you participate in, and then let's learn about the Lucas Museum of Narrative Art.
Uh, Thanks, Timon. First of all, thanks for having me on the platform, and it's a pleasure to share as much as I can, at least on this confidential project with the rest of the group. Really quick. Background. I originally come from a bachelor's of engineering, and kind of like switched to architecture. And now I'm basically with Walter P. Moore, almost approaching the 5 years mark, and I'm part of the enclosure engineering group, as you mentioned, which is a subgroup of the structures engineering, and I focus. My specialty, as I guess, is a digital designer. So I'm residing in Los Angeles, so I'm probably gonna be using the like word probably too many times. Okay,
and you work on some of the craziest buildings, don't you?
Yeah, sure. I mean, through my experience, through my kind of like work career, it's been a fascinating journey. I have to say that from hotels in Azerbaijan to complex Disney projects to projects like Lucas Museum, and now I'm focusing mainly on the kind of like the typical enclosure engineering. Doing some more traditional facade project. That's exactly what basically these timelines are showing to us. They're not necessarily linear, so that's why I'm saying A and B. Basically, the one kind of like timeline that I was mainly involved was mainly evaluating the surfaces and kind of like the surface that we were seeing from the architect, and kind of like doing this back and forth between us, making sure that their fabrication ready, and at the same time making sure that the architect was happy with the deviation that those resculptured surfaces or
so you would get a surface and then you would try to make it more constructible, more buildable, and then you would provide it back and say, did we meet your design intent? Is that what you're saying?
So yes, yes, I'm saying that, and that's one part. But as a lot of people that have worked with architects, so the main aspect of that first timeline is that the architects are usually using software that allow them to sculpt some surfaces, right? But those surfaces, when they're sculptured, they're not necessarily ready for fabrication. So our task on this specific part of the project was to evaluate the surfaces, make sure that they smooth enough, so any breaks in the continuity of the curvature that could be seen from the human eye when they're fabricated do not exist, right? But once you're resculpturing a surface, you want to make sure that the deviation from the original surface is not that high, right? So you're not basically affecting the design. You're basically developing the design. You're not affecting it in a sense that you're alternating, right?
Mm-hmm.
So that was the focus on that first aspect of the project. Was that clear? Did that
I think
respond
so.
to your question? Okay. Then the second timeline is, okay, you're sculpturing the surfaces, and that's in a sense going on. But on the other hand, you have to have some tools to change between the design and the engineering software, right? So basically, as we all know, there's as much as you can do within the Rhino grasshopper, as you mentioned earlier, environment. But when it comes to heavy engineering, you need to understand how to properly mesh any surface, and not only properly mesh it for FEA analysis with the final element analysis, but also add features to that mesh, as I'm saying, like over there, which is basically the tertiary steel and the secondary steel that basically link the panel ribs back to the primary structure, right? Hopefully that's clear as well. Correct. That was a question for you, Tim.
Oh yeah, I think so.
Okay. All right. Starting the presentation, I'm going to focus a little bit as I mentioned on the sculpturing of the surfaces by the architect, and what this back and forth would look like, and how then we would evaluate those surfaces and make sure that they're on the right track for fabrication. So, one of the things that always come to mind when it comes to architecture is how you can actually widen the spectrum and go and look what other industries are doing, where you need like high fidelity of surface treatment, and so basically take a concept that applies to, in a sense, smaller objects, could be like cars or like jewelry. So in a sense, higher definition of surface quality, and then in a sense scale them up, right? So that's exactly what we did. We basically looked at what the automotive industry is heavily leaning on, and we realized that they have been using those what they call diagnostic shaders for the curvature continuity, and those are basically the diagnostic shaders are basically two big groups. The one is the horizontal and vertical, which are also known as zebra stripes. And so basically, you're basically shooting a surface with basically like a bank of strip lights, and you can either have those bank of strips either vertically or horizontally. And then the second one is basically the ISO angle, which what you're doing, you're basically moving that bank of strip lights along the surface. Well, we basically used mainly the zebra stripes for the evaluation. And I'm gonna just really briefly explain what the zebra stripes are, because it's basically a method to understand the curvature and continuity between two adjacent surfaces. And if anybody looks those up, there are basically three kind of like main categories of curvature continuity, and in a sense, there is a prerequisite, so which means that for you to achieve curvature of, as you see on the screen, G2, you need to have G0 and G1 already tackled. So basically, I'm gonna again briefly explain. So G0 is basically the lowest continuity level, and basically measures the gap between the two surfaces, right? So if you have a gap, you can see that basically how the zebra stripes are broken in quotes. And so moving the G1, it's kind of like a more higher level curvature continuity as G0, and basically the way it's easy to understand it is basically not only the two faces meet, which means that the G0 is satisfied and at a common edge. At the same time, the tangent plane at each point of this along of this edge is the same for both faces and
So G0
surfaces.
they're touching. In
Mhm.
G1 they have the same. I'm getting a little too loud. Sorry, guys.
No
At
worries.
G1 they have the same curvature or kind of
They,
direction at that point, and at G2
right,
they have that reflective smooth look. Um,
right, and yeah, I mean it's so basically the G2 is also called radial continuity, and basically not only they're meeting, not only they're tangent, not the two surfaces not only are meeting, not only the planes are tangent, but at the same time the rate of the curvature change along at this edge where they're meeting is the same for both surfaces and faces. So it's kind of like a level, and curvature G2 is basically what they call the A level of alpha level of curvature continuity, which is basically what we're hoping we're aiming for, right? We don't want any breaks on the surfaces when they come together. So because imagine like we're talking about panels that are really big, um, and so any difference in the curvature between those panels when those two panels meet can actually and the way the sun hits those surfaces can be visible from the human eye. So you want to be careful when you're evaluating your surfaces, and you need to understand that kind of like curvature continuity principles in a sense, right?
so it's not just
So
like surface continuity; it's also curvature continuity, which gives you that smooth reflection like you would see at the Bean in Chicago, and now maybe in this museum.
correct. Um, so so here I pulled up some examples from for you guys. On the left hand side, we have the original panels, and there's two tools that you can use within the Rhino environment. The one is the zebra stripe, and the other one is the environment map. And the environment map looks like a more of like a beam of light that you can that it's been reflected along the surfaces. But for instance, on the left-hand side, you can see we like on the original surfaces, you have breaks at the even within the panel, right? So which means that the kind of like the curvature within the panel is not well defined. And so you can see after the treatment that we went through, that now the discontinuity within the panel panels are now resolved, right? And if anything, you kind of like want to push that discontinuity on the panel edges because there's also a seam. So it's again like it's all like the amazing thing. It's all like on the eye of the beholder in a sense, right? So you there's always a visual check, and there's different. We had different people checking for these discontinuities at different levels, because if you spend looking at a zebra stripe on a building for, I don't know, maybe like a couple of weeks, then you just basically sit that on in your sleep. So we had different people kind of like doing the back check and making sure that the results are acceptable for different specialists, if you will. Um, and and so one of the things that I wanted to bring out is kind of like the garbage in, garbage out idea, right? So the one of the things that you have to be careful, and you can already see that there's not going to be curvature continuity if you have a good surface, right? And even your isocurves, you can see on the left hand side there were we were receiving them in a sense kind of like jumbled. So we have to, in a sense, rebuild the surface, make sure that the isocurves um, uh, are tidy in a sense, right? And that I was actually was reflected in a sense when we're using the zebra tool, right? So that the reason for us going and rebuilding the surfaces was basically to stop these discontinuities you can see on the left hand side, which are pretty big, right? And you can see how on the right hand side those have been smoothened out. So how do you actually reshape a surface For the simpler panels, what we did is that we basically went with a simpler approach, right? So we said, get the panel boundary, so we know that basically all adjacent panels are actually satisfying this all this, like the boundary conditions on four sides of that panel. So we're not really moving the panel out of its place, right? And then basically we would segment this panel along one of the boundaries and get sectional curves and then sweep that panel. That is one of the approaches that someone can use. The one thing that I have to say on that aspect is that basically it wouldn't be for a surface that needs really you really need to control the deviation from the original surface. Could not be the ideal tool for that, but for the majority of the surfaces and architectural surfaces, that could be a.
You can just take the surface, slice it through with a bunch of planes, find those curves, and then just make a new, rebuild that curve. And for those who are grasshopper savvy, what are your favorite curve rebuilding nodes? I don't know if we're going to get live into grasshopper messing around or not, but maybe you can at least share that.
Yeah, I try to stay away from that, mainly because every workshop or / presentation that I've done online with Rhino ends up in in chaos. So that's why I've made for you what I did on this presentation is that I pulled up some videos of me doing some work and also found videos that could help the viewers understand a little bit what each tool is doing that I'm going to show. This one was a little more self-explanatory, Timon. That's why I didn't really, in a sense, pull any videos. But for the next tool, which I was really excited to see in the works, and I have a video to show you guys, is basically the surface reconstruction using XNURBS. And that's basically like an add-on for Rhino.
I haven't used XNURBS, so that'll be cool.
Yeah. So let me. For a second, I'll just close this presentation and show the video, because we can solve really complex problems in engineering, but like adding a video in a presentation when you're doing InDesign is more complex.
Well, while you do that, for those who are watching this with the comments below or in the chat over there, tell me what your favorite ways of rebuilding meshes are. Have you ever rebuilt a mesh? Do you have a favorite curve, favorite node, favorite add-in you've used? Let other people know about it, either below or to the side. All right. Well, you pulled it up.
Let's see what we're Timon, you're saying about rebuilding surfaces, but yeah, we'll get. You're so eager to get to the meshing part, which we'll get in a second.
My bad. Rebuilding surfaces. Don't want to get ahead of my game. Sorry, I'm using the wrong words here.
It's okay. We're all excited. It's fine. So yeah, this is how basically XNURBS works, and it's a really powerful tool. I'll play the video in a second, but you can basically select the boundary curves, and you'll see how you can add the boundary curves, and then you can control the curvature continuity. If you can see, it has like G0 precision, G1 precision, and also at the same time have the zebra preview. So it's kind of like all-in-one type of deal. So that's why I think it's a really powerful tool for people that really want to have a good control over the surface quality that they're rebuilding. So here you can select your boundaries, and you have already defined that you want the G2 continuity, as we said earlier. So you recreate it. And let me just pause it here just to show the zebra, right? So once it pulls out the zebra for the whole thing, right, you can see basically you can't even understand where the joints of the new surface that you rebuilt are, right? So the continuity, you can see how the zebra stripes are really smooth. It's a really powerful tool. I know it comes with a cost, and it's unfortunately not free for Rhino, but it's definitely worth it for people that want to do this kind of curvature surface rebuild exercise. So I strongly suggest that. Okay, let me go back to my presentation. So moving from the surface reconstruction, we're basically going to kind of like as I said, the B timeline, right, where surfaces are being translated to meshes and engineered on. We actually use Strand 7 to apply all the material properties and run the analysis to understand the displacement. At the same time, as we're figuring out more the connection between the secondary and the primary, we're adding features to these meshes, which would be, in a sense, any stiffener, any pins that need to be added to the mesh to make it stable. So I'm just basically showing a little bit of an exploded axle of the FRP buildup. And you'll have your FRP panels and your kind of like backup structure. So, and that's kind of like a close-up of, and I'm explaining basically what do those features mean in kind of like the modeling aspect, right? So you have a mesh, but at the same time you're not really like meshing just the panel itself. It's not really doing anything for you. You need to understand how basically how the forces kind of like are being translated back into the backup structure. So you need to be adding elements to those mesh and understand the load transfer. So I know that the spectrum of the audience in this platform is pretty diverse. So, and one of our colleagues, Timon, actually told me that a lot of times when you're talking with in a crowd of like a mixed bag crowd, you have to assume that they know less than you're actually showing. So in a sense, I just wanted to put a couple of slides. Why are we using those meshes? So people that are already aware of those, forgive me, but people who are not, I'm sure that they're going to get something out of it. So basically, the basic idea of the finite element analysis is that you can't really run a finite element analysis in an infinite degrees of freedom which a surface has, right? So you're basically taking a surface and you're breaking it in smaller pieces, which now it's kind of, in a sense, finite number of points and finite number of elements that you can run and that's why the finite element analysis comes from. So there's a lot of mathematics involved behind that. The way I like to think it is basically it works. The meshing works basically as the integral works. So if you have, but in 3D, right? So if you have a curve, you basically want to approximate this curve by dissecting it in straight segments, right? So that's the same concept, but it's just if you take it in the 2D domain, right? So so you're basically creating discrete elements that then you can analyze. And like just trying to simplify, explain this concept is I have like a triangular mesh just to explain how that, the components that kind of in a sense create a mesh. And you have the node, which is basically those vertices. You have the edge, which is the line element. The face of the mesh, and then a face normal that basically shows the direction of we all know what a normal to a face is. And like I'm including another really quick in a sense quote of what a mesh is. It's basically a subdivision of a continuous geometric space into discrete geometric and topological cells. I really like that description. So I'm sure that a lot of people that have tried to to mesh anything, they have been scratching their heads. There's a lot of tools out there that, in a sense, do the same thing or not necessarily not. And there's a lot of grasshopper tools. The native meshing tools, the Mesh Plus. There's the Kangaroo stuff, which everything is great, and I feel that everything has its place. What I was really happy to find is that, and for me was a pretty exciting kind of, in a sense, upgrade, was that Rhino 7 came up with the Quadmesher, and it's a really powerful tool. I can never like really explain how powerful this tool is. It's the really powerful thing that this tool offers is basically its simplicity. And I have another. It's more of a advertisement video that shows how it works. It has some, not necessarily architectural elements, but it was pretty cool to see how by using this tool you can actually simplify those some really, I would say, bad meshes, but in a sense, you can clear out your meshing like pretty easily. And it comes with a settings component where you can basically change the density of that mesh, and you can also add guide curves if you specifically want specific curves to be added in your mesh. And it's a pretty handy tool. It's kind of like really as simple as it gets. And honestly, because meshing is always a step between surface evaluation and engineering, you kind of want to have it as simple as possible, right?
And you're losing a lot of detail when you go about that?
No, because it also has, if I'm not mistaken, it actually has a way for you to control the deviation between the original B-rep and the final mesh. So they've done a really good work of you being able to control the quality of the mesh. So I would say that the deviation wouldn't be noticeable.
Yeah, I was just using that just the other day and generating an analysis model. So it's good to see that you approve it.
Yeah. And the Quadmesher goes hand in. So one more step, which I'm not really necessarily showing here, is basically when you triangulate the mesh, right? Because a quad mesh could be flat, but not always. You actually if people have used Karamba, for instance, which is native in Grasshopper, not native in Grasshopper. I mean, you can work. It lives within Grasshopper, whereas Trans 7 doesn't, for instance. You need triangular meshes. So that tool with the triangulate mesh tool, it's really like it's a pretty powerful tool. So that's why I'm saying hallelujah. Like honestly, for me, it was a big step on that meshing part. And a lot of designers are scratching. I come from, in a sense, a designer background, and it has always been a challenge to find the correct tool for the right mesh. Let me just put this back on the full screen mode. Okay. So you have your mesh, as we said. Like we were heavily leaning on the Quadmesher at that point, and as I mentioned earlier, one of the, in a sense, second steps is okay. You have the mesh, but then you have to add your stiffeners, you have to add your pins, you have to add all these points, and so basically you have a mesh, but you want to control this mesh and do like a little bit of surgery, in a sense, like local surgery on the mesh to manipulate it in a sense that is usable for your FEA and final element analysis. And so I have a video of a simple concept. Again, I didn't want to create to make things look so complex. So it's a simple concept that when it's scaled up, it's pretty powerful. I made another video for that, where you basically start with your panels as B-reps. You start with your tertiary steel, and so the first thing is, of course, as we said, like you can meshing your B-rep with a Quadmesher to come up with a clean mesh. Then you basically extending your tertiary steel to ensure intersection. You're deconstructing the mesh to get its vertices. And you can, just to keep the mesh layout consistent, what you can do is basically find the closest mesh point or mesh vertex to that point that you just found when you're intersecting your tertiary steel with your mesh, and basically just do in a sense a replacement, right? So then you at least you can still in a sense triangulate that and always in a sense come up with like triangular meshes. So that was another concept that's pretty powerful. We kind of like lean on it a lot.
And
It's a
you're
simple
not able to
concept, but
mesh it with like guide points with the
you can.
Quadmesher, where you are definitely want to hit specific points and Quadmesh. Would you have to split the surface first, or?
So you know how again, I'm not an expert in meshes,
Mhm.
but thinking right now is, you know how a mesh is always defined by so when you're basically looking at how a mesh looks like, there's a sequence that each phase has like basically a sequence of like it's Q1, Q2, Q3, Q4, right? So basically like
Mhm.
a 4 point phase is defined by a sequence. So it's always kind of hard to break the sequence, right? And say, oh, actually, I want this point in that sequence in order to not come up with crazy overlapping meshes, right? So I personally feel, and that's my, I think, it's a subjective question, but what I personally feel is have a clean mesh and then do a little bit of surgery,
Mhm.
and that for me has worked
That like
pretty
microsurgery around the
consistently.
point is easier than like having lines that go through your like support points and then meshing around those specifically.
Right, and again, I'm just because you don't want to break that kind of like mesh
The
vertex
pattern, yeah, the vertices and
vertex
the way the
pattern, right?
vertices all
Like a
line up in
series.
that mesh. Exactly.
Yeah. And I'm more than happy if people want to suggest something else. That would be great. So I think I'm approaching to the last slide of my presentation. I hope it has been interesting for the majority of the people. But so I found online, and just because as I mentioned earlier, the kind of like the Lucas Museum is more of a confidential project. I just wanted to show to the group here what like the basically um the scale of those panels, right? Because we're so used of like rotating around, zooming in, zooming on, and play around with the buildings like they're basically objects that can live on our desk. But in the reality, those panels are huge, and there's a lot of work going into them. So basically, going like from 1, 2, 3, 4, you can see how the mold is created, right? And those molds can take up to like 12 weeks or so, or even more. This is actually from the Dior flagship store in Seoul. You guys are free to look it up. It's a pretty cool project. And basically, so once the FRP is in a sense casted, then you can see how it comes up with a backup structure, and basically it follows that principle of the in a sense like unitized curtain wall, right? So yeah, that's what I had to share with you guys today. Again, I'm sorry if I couldn't show more. I'm sure most of us are working with projects that are confidential. I try to keep it generic, but at the same time show you what we did, things that we've learned, and yeah, I'm
Yeah, it's
open to
interesting to
any
see
questions.
how this idea of meshing can carry. I mean, obviously, it carries over from project to project, and you learn and you grow. And I do think I know the zebra stripes have been something that are really helpful. Um, and yeah, all right. Well, I'm looking at the chat here. If you have any questions, I'm looking here, and as they come up, I'll try to shoot them over. we'll stay live for a few minutes after questions go dead. So as long as you guys keep asking, we'll keep answering. And I see a couple jumping up here. So first, what's the best way of triangulating a quad mesh? Some GH plugins give weird results, flip diagonals, etc. What are your thoughts around that?
The triangulate tool that is native to Grasshopper, I think it has been pretty consistent for me. I know Weaverbird has some additional tools for that. Like it's Giulio Piacentino, right? Weaverbird it's a really cool tool that for me has been used super helpful. It also has the ability for you to thicken the mesh, which is, I get it, it has been under development for a lot of years, but if your mesh is quite simple, and thank God with the Quadmeshers, your meshes are simplified enough, it can work in a pretty consistent way. Yeah.
One of the other people in the chat, Horse, said that to try the Ngon remesher. I don't know if you've used that.
No, and I'll jot it down just to.
Look at that. We're all teaching each other all together. I love this.
That's exactly how this works.
Those molds, the one that you were showing on the screen, do you know more about how they were constructed? Do you think they used CNC?
I can't really speak to that molding. It goes back to the fabricator. We're mainly involved on the on kind of like the end result and making sure that the surface quality is adequate and up to our standards. But yeah, so I can't really speak to that. I can bring back the presentation or I can follow up with some.
I've caught the last screen you had, so I'm showing that again.
Okay. Okay.
All right. Let me see if there were other questions here that came up as we're going. You have huge kudos. Someone said this is the best presentation they've seen on this topic, so thanks to you for that. And I'm not seeing any other questions. Let me think here. What else I'd like to ask, and then we can just close. Rhino or Grasshopper? What's your preference for working with meshes and surfaces? When would you choose Rhino, and when would you choose Grasshopper?
So in general, like I think, okay, I don't think there's a simple answer to that in a sense, but
those are the best.
What I really try to avoid doing is using Grasshopper without having a plan. I'm not necessarily replying to your question, but I just wanted to share like a principle, right? So so in a sense, for a lot of people that don't really use heavily Grasshopper, that's in a sense a misunderstanding. So Grasshopper is basically grabbing what a Rhino commands, right? Mm-hmm. So there are some Rhino commands that haven't been exposed yet to Grasshopper. So it could be that something lives in Rhino and doesn't live in Grasshopper. So I would definitely try even the simple commands in Rhino, make sure that the capabilities of Rhino are not met, and then because a lot of people think that if I go to Grasshopper, then I'm gonna, magic happens. Magic happens, but it's in a sense it calls like functions of Rhino. So to maybe I can respond to your question saying that basically Rhino has a bigger library, if you will, right? And then Grasshopper has a little bit more of has a snippet of that library. I think they're kind of like growing together now, but for the I think as a heavy user yourself, you would agree that in the past, when we started using that, less and less there were actually commands in Rhino that were not available in Grasshopper. So to answer your question, I would start in Rhino, make sure that whatever I need or things that could help me are available or not, and then if they're available, then I'll just check Grasshopper to see if I can scale that command in a parametric environment now. All
right, with no other questions, I'll ask 2 more and then we can close. First, how did you get into first, if actually reverse the order, what would you recommend for someone who wants to learn how to do this type of work? What would you recommend they learn?
Again, like as a visionary like you, I always try to tell myself to look outside of your comfort zone, right? So if you want to, there are other industries. There are other, especially in this type of work, there are other industries that are way ahead of architecture, right? So the car industry, the naval industry. So there's a lot of like
Aerospace.
this aerospace, correct? So there's a lot of industries that where the surfaces and the surface treatment and all of those really high fidelity innocent surfaces are more critical there rather than architecture, because let's face it, right, in architecture you can design something great and the fabricator might screw that up. So in a sense, there's a little
Nothing
bit of a
against our
lesson.
fabricator friends. We love that they can create lots
Of
of these
course,
things.
I'm just saying, right? Like I think the milling process on like sculptures or spaceships is way more advanced. That's all I'm saying. So, um,
All
yeah, I don't know
right.
if
Last question then. How did you get into enclosure engineering or enclosure design?
So I've been always fascinated by crazy shapes. I don't know. It just comes to as a personality. Just coming from a heavy mathematical background, I was always intrigued by complexity. That I was fortunate enough to be able to translate that into architecture. And so, kind of in a sense, I didn't end up. It kind of like found me along the route. So yeah, hopefully
Yeah.
that was helpful.
All right. You get to choose which project because I don't see which one. But the last question, which is actually coming from the chat here, is how many iterations did it take you before you got it just the way you wanted on the surface? And you can answer that from your own or from how many iterations of different design and sculpting, because you talked about how you were getting different sculpted designs. So take that wherever you want. But how many iterations did it take from initial concept to actually getting it to be fabricatable? Or yeah.
I can't really pull a number out of my head, but I can tell you that I had enough iterations and the rest of the team enough to give us PTSD. So, it's, in a sense, we're sleeping and we're like still thinking of oh my God, like the surfaces are coming back.
Yeah,
It has been an interesting process. Sorry to yeah, joke
definitely.
aside. It has been an interesting process. There were a lot of iterations. Architects are, designers are always changing the shapes. You have to reevaluate. You have to redo the same process. So you have to have this process nailed down in a sense, right? So in order for you to adapt fast to the design changes, right? And that's the important thing.
Yeah. Well,
Yeah.
thank you so much for coming on the Your Desk University
Thank
show.
you for
Thank you
having
for
me.
all those who are participating. And we look forward to future chats down below. And with that, I will close. So thank you, everyone, and we will see you later.
Thank you, everyone.